So we recently learned the first derivative test, and remember, the first derivative test allows us to decide where a function is increasing or decreasing. This is hugely helpful. You could imagine if you had a profit function, you would want to know under what conditions is your profit function increasing and under what conditions is your profit function decreasing, so you can make smart choices about your business. Well, look at our example here. We have two functions graphed here. We have the parabola y equals x squared, but only where the x's are positive, so I've restricted the domain. So we've got our typical parabola that we're used to seeing here, and then I've got the function square root of x, right here. So here's our square root of x. Now, both of these functions are increasing. So if we apply the first derivative to both of these functions, we're going to get that they are both increasing from 0 to infinity. Okay, and that's helpful to know, but as we can see from this picture, there's more to the story, right? If you were given a choice that your revenue could grow next year for your company like this, like x squared, or your company could grow like this, like square root of x, both would be good, but you would much rather have this rapid growth increasing your company faster, right? And that's really what the difference between these is going to come down to, and that's what we want to be able to figure out. How can we come up with a way of comparing both of these increasing functions in a way that gives us more information about how these things are increasing? In what way are they increasing? Think about a line here. Well, a line is always increasing at the same rate, right? For the whole piece of that line, anywhere you calculate the slope, you're going to get the same value, all right? So things that you could think of it as things that grow faster than a line and things that grow slower than a line. And that's kind of what we have here, at least over in the long term, right? There's this short period where they kind of have the x squared is growing slower than the square root of x. But once we pass that initial 1 point, these functions behave very, very differently. So as you can see, if we were to calculate the successive tangent lines along this curve, y equals x squared, what we would see is those tangent lines would be getting steeper and steeper and steeper. In other words, the rate of change is increasing, right? So you have to think about this on a couple levels. The slopes of the tangent lines being positive are telling us that the original functions are increasing. But if we look at the fact that the rate at which they are increasing is increasing. That's what we see here on the x squared. The rate of increase is increasing, right? It's happening faster, right? Whereas here, the square root of x, if we look at the tangent lines, the rate at which this is increasing is actually slowing down, which sounds a little weird when you say it that way. Our rate of increase is decreasing. Yeah, so you're getting faster, but you're getting faster at a slower and slower rate, okay? So we bring in this new concept called concavity. Now, a lot of times we already have an intuitive definition of what something like concavity would mean, but in order to use it in mathematics, you have to define it precisely in mathematical terms. So, if you think about a shape being concave, you can kind of draw something inside of that shape. That's where the part is concave. Well, we're going to specify shapes being concave up or concave down, right? And so you might already kind of guess which one's going to be which. So if we've got our x squared function here, this is what we're going to call, so let's get rid of this one. This is what we're going to call concave up. The concavity is on the up side of the function, whereas this one we're going to call concave down. The concavity is on the downside of the function. So that meets with our intuitive definition, and yet how do you mathematically prove where the concavity of something is? So we still have to be even a little bit more precise, but we have a nice tool. So here's a way to think about this. Let's go back to our function that was concave up here. So we've got our concave up function, and then we've got our tangent lines. Right? So what do we notice about these tangent lines as we move things around here? The tangent lines all exist below the function. See how the tangent lines are on the underside of this function here? So this is how we define concave up. If your tangent lines are below the function, then you're concave up, which makes sense if you kind of stop to think about the shape of a concave up shape, your tangent line should be below. And we get the same thing with our other function, just sort of the opposite definition, right? Here we can see that our tangent lines all exist above the graph. So this is what we would call concave down. So you want to think about that, make sense of this, because again, you don't want to go memorizing stuff in calculus. You want to just understand how to think your way through these problems. Well, yeah, if my tangent lines are doing this, then my shape kind of necessarily needs to be concave down. If we're talking about a nice, smooth, continuous curve, right? Here's how things are going to go. So that's how you will decide when something is concave up and when something is concave down. And then you always want to have in the back of your head this understanding that if something is concave up or concave down, that is indicating to us some information about the rate of growth at that piece. And you can use concavity to make decisions about things. So let's take a look at our next example here. So let's take a look at our next example. Here we have a function where right over here, our function is concave down, but over here, our function is concave up. So the concavity changed at some point. Looks like that point is the origin, 0, 0, and that's in fact true. On this side, we have concave down. On this side, we have concave up. It's usually a lot harder to tell where that change is in concavity, but we'll be able to figure it out exactly using algebraic tools. So this point where our concavity changes is called an inflection point, right? And inflection points can be helpful, right? Like if you're running an ad campaign and you're getting a bunch of business from running that ad campaign, but then later on in the campaign, you're having to throw more and more money to get the same amount of benefit that you got before. Basically, like you might hear the term point of diminishing returns. That's an inflection point. So the point at which your curve goes from something like this, where you're having really extreme growth, to now, like we saw with square root of x, where it's leveling off. You can still pay more for that ad campaign, but you're going to get less and less viewers or sales or whatever it is that you're measuring over time. So usually once you hit that inflection point, it's time to turn off that ad campaign and then spend that money elsewhere that's going to get you more of a return than that diminishing returns point. Okay, so these inflection points can be very, very helpful in determining certain types of problems. And here we see an even more interesting example of this. So here we have a function that's increasing up to this point, and it's increasing from this point up to the top, and it's decreasing somewhere in the middle. But notice that our concavity frequently not going to line up with where we're increasing or decreasing. Our concavity is different. So we're only increasing up to this point, and then we start decreasing, but our concavity, right, this whole piece is concave down. So in one piece that's concave down, you can have both increasing and decreasing parts of your function. Same thing we see over here. We have parts of this side that are both increasing and decreasing, and yet the whole thing is concave up. Okay, so we'll want to look deeper into things and figure out where that is. So if you think about it in this way, right, the way we described it a few minutes ago, the derivative gives you the slope of the tangent lines, right? The derivative is giving you the rate of change of something. Well, what if we take the rate of change of the rate of change? Well, that's exactly what a second derivative is. You're measuring a rate of change of rate of change. Is that rate of change increasing? Is that rate of change decreasing, right? If you just take the derivative, you're really just figuring out the increasing at a point, right? Are we increasing here? What's the increasing, decreasing nature of this? But if you can kind of go one step further with this, you're looking at the rate of increase of the rate of increase, right? You got to think about it for a little bit. It sounds weird at first, but once you get it, it's really helpful in trying to understand these kinds of problems. Okay, so let's dive into an example and see what's going on here. So our function here is x cubed minus 4x, and we're actually going to go through using the second derivative. We're going to break down how the algebra would work on a function like this, and then you'll start to make sense of the second derivative test. What does the second derivative tell us, and so on. So we'll take a look at that. All right, so we're starting off with the function that we were just looking at, x cubed minus 4x. Well, we now know that there's information that can be gained by using the first derivative, and there is information that can be gained using the second derivative. So if we're going to get that information, we're going to need the first derivative and we're going to need the second derivative. So that's kind of the way you should start these types of problems. First thing you do is go through and figure out what the derivative is and then figure out what the second derivative is, because we want to take all of that information and use all of it. So if this is a straightforward polynomial, x cubed minus 4x, if I take the derivative, I get 3x squared minus 4. Take the derivative again, I get 6x. So I've mentioned this before, and it's a mistake I see all the time. It's a mistake I occasionally make on my own if I'm not paying close enough attention. We've now got 3 functions in this problem, and they all have the letter f in their name. So you really always want to make sure whenever you do an operation, make sure you're grabbing the right function. It is very easy for people to use f when they mean f prime, or use f prime when they mean f. So you really have to understand what each of these functions is actually telling you so that you can know when to use it appropriately. You can use it at the right time and then not accidentally grab the wrong function and go from there. So we're first going to apply that first derivative test. So we've got f prime of x is equal to 0. Well, we can just fill in what f prime of x is actually equal to, and that derivative is 3x squared minus 4 is equal to 0. Right, figuring that out. So then we can go further with the problem. So 3x squared is equal to 4. Then we divide both sides by 3. We get x squared is equal to 4/3. And then we solve for x. Remember, we're going to end up with a plus or minus here, so that's a common mistake. People take the square root of both sides and think they're just getting square root of 4/3. You get 2 values. You get plus or minus square root of 4/3, which if we simplify would come down to 2 over square root of 3. Now, depending on what you're going to do with this answer, you could rationalize the denominator, but for the way we're going to use it, it's not really necessary that we rationalize the denominator. So if you're doing a homework problem, double check how they want the answer given. If you're doing a real life problem, it's kind of up to you whether you want to deal with this as 2 over square root of 3 or 2 root 3 over 3, right? Whatever. But the key is that's where these values came from. We took the first derivative, set it equal to 0, and solved, because we know there's no undefined points since this is a polynomial. If there were undefined points, we would want to include those in our values down here. So we just get these 2. And then we're going to go through and construct our sign chart. So then we go through and construct our sign chart. So we just got that these happen at -2 over root 3 and 2 over root 3. So then you would go through and test your intervals. We get positive over here, negative over here, positive over here. So then remember, we use the derivative to get information about our original function. So our conclusions are not about the derivative. Our conclusions are about the original function. Okay, so make sure you're careful when you're writing out your conclusion. F of x is decreasing from -2 over square root of 3 to 2 over square root of 3, and it's decreasing from -infinity to -2 over square root of 3 and 2 square root of 3 to infinity. Okay, so we've now used the first derivative to categorize for us where this thing is increasing and decreasing. And notice the pattern here. We had a function that went from increasing to decreasing. Well, in most situations where you go from increasing to decreasing, you probably have a maximum right there. Then we went from decreasing to increasing. We probably have a minimum right there. Okay. So that's likely going to be our minimum. Let's jump back over to the graph, and it looks like our values are probably matching up with what we just got, right? You can throw that 2 over square root of 3 into a calculator, see what you get, and it looks like it's matching up with our values right here. So everything looks good so far. Like I would encourage you to regularly do that when you're doing calculus, because once we start throwing the first derivative test, second derivative test, all this other stuff into one big problem, you want to be routinely looking back at your graph and making sure that the algebra you're getting matches the graph. Otherwise, you're going to work on a problem for 15 minutes and then realize that, oh, I made a mistake 10% of the way through the problem. You just lost a ton of time. So always go back and just draw this connection between the algebra we do with the calculus and the actual picture, right? Plus, it's going to help you learn the calculus a lot better, and you'll get to where you have a much greater intuition for these types of problems. Okay? All right, now we're going to go through and see what we want to do about the second derivative, right? What can that tell us? Okay, so now we want to apply the second derivative. This one is super easy. So we take our second derivative we found earlier, which is just 6x, and we set that equal to 0. Again, if there were undefined values, we would include those in our sign chart. But here we get that this just happens at x equals 0. So our sign chart's pretty straightforward. We split the number line at 0, and then it's pretty easy to see here. If we plug a negative value in for x, we're going to get a negative number. So we're negative over here. If I put a positive number in here, I get positive, so we're positive over here. So this is telling us, our conclusion is that f of x is concave down from negative infinity to 0, and it is concave up from 0 to infinity. So again, let's look back at our graph and see if that makes sense. Yeah, looks like it. We're making the claim that this whole piece is concave down. Yeah, that's believable that this piece is concave down. And we're saying this whole piece is concave up. Yeah. That looks legitimate. It looks like that's concave up. So we have classified this graph in pretty good detail. We know exactly when this thing is increasing and decreasing. We know exactly when it's concave up and concave down. That's really helpful information to know about this kind of a thing. I'll throw around the term second derivative. Formally, the second derivative, if you look it up in the book, talks about when your first derivative is 0. So if you know your first derivative is 0, that means you're getting a horizontal tangent line, so probably a max or min. But if it's concave down, then you know you're going to have a maximum. If it's concave up at your horizontal tangent line, then you know you're going to have a minimum. Right? So this is one way of identifying your maxes and your mins. The problem is there's a breakdown. If the second derivative is also equal to 0, then it's not going to tell you much. And in practice, most people use the first derivative to tell where something is increasing or decreasing and to classify their maxes and mins. But occasionally it can be helpful to use this second derivative test to see if there's a max or min there. What's usually more helpful is you use the first derivative test to answer everything that you can. Increasing, decreasing, maximums, minimums, all that kind of information. Then you go to the second derivative test to tell you about concavity. Is it concave up? Is it concave down? All that kind of stuff. That's usually what ends up happening when people are doing problems, okay? So, when I throw out the word second derivative test, I really just mean anything you can figure out using the second derivative. The book is a little bit more strict about what they call the second derivative test, but really it's just throwing the second derivative at something and seeing, is it concave up? Is it concave down? Can we tell any more information about the graph than we couldn't already? You can think of that as being that second derivative test.